So good morning and welcome to our featured panel on GPU computing with OpenMP and OpenACC. This is intended to be an entirely interactive session. I have prompts for our panel, which I'll introduce in a second, but most of the people in this room have experiences that they might wish to share and also consult with the people that are on our panel right now. So actually, first I'll introduce them. So we have Jeff Larkin, and Jeff is NVIDIA's representative to both the OpenMP and the OpenACC technical subcommittees. Next to him is Michael Wolf, who is, well, both a senior compiler engineer at PGI, as well as the head of the technical committee for OpenACC. And lastly is Fernanda Foretter, and she's from Oak Ridge. And Fernanda is a staunch champion of getting GPUs to work inside of Titan. So I think her experiences both in doing that as well as in running some of the more recent hackathons are something that we might want to poke on during this session. So, so that's the purpose of the session. And I'll start with a question, and then you guys can take it any way you like in the room, please. So that's what this mic is for. Oh, and I guess my name is Duncan Poole, and I work at NVIDIA and on OpenACC and many other things in the tool chain. So Jeff, why directive? Well, no, let's start with a little more fun one. Should I wait for OpenMP?
No, that gets asked a lot, actually. So one of the things that we get asked a lot about is, OpenMP has accelerated directives in the standard. Why aren't we using them? And frankly, OpenACC got a pretty darn good head start on OpenMP. They had about a 2-year head start on designing directives for GPUs. There's a lot of work happening, cross-pollination between the two sets of directives. But at the end of the day, what we have is a directive set that is, say, 2 years more advanced in terms of GPUs and parallel processors than OpenMP. And so, yes, OpenMP is coming. You will be able to, I suspect this year, I've heard promises at this conference that this year you will be able to run OpenMP4 on GPUs. I don't think you should be waiting, though. OpenACC is available now. There are several compilers. It's well tested in several tools and is available to you. So begin using it. And the thing you'll learn is that the hard part is not in how you spell the directives. The hard part is in making your loops parallel, making your data remain local. And that is transferable knowledge. So you'll be working on it now. OpenACC is a great tool. I use it daily, and be using that. Don't wait.
So you said cross-pollination between the two organizations. So what does that mean?
So if we look at the membership of OpenMP and the membership of OpenACC, it turns out that it's a kind of a pretty Venn diagram. There's a bunch of us who are paid members of both. There's many of us in the technical committees that attend both, from Cray, from NVIDIA, from AMD, from PathScale, that are attending and designing both. And you have OpenACC moving very quickly to try to address a very laser-focused set of challenges. We want things to run well, performance portably on a wide range of devices. And then OpenMP, who has to take a more cautious stance, and they have a more broader scope. And so things take a little longer, and they'll get there. And so we're learning from OpenACC and OpenMP, and a little bit in the other direction, as you pointed out yesterday. But there's a lot of work from both bodies.
Okay, thank you. I'll ask a question from Michael, but please raise your hand if you have your own questions. This is just my way of getting us going. So user experience, Michael. What should we expect will improve the user experience over the next year? We heard from Christian a little while ago about how C++ has been improving, but where do you see it going?
Christian's talk. I was at CSCS presentation. But so user experience, what would help in the user experience? And for those of you who were not at Aaron Vos, his presentation yesterday, I'm going to have to get out of the echo zone.
A little feedback.
So Aaron gave a great talk yesterday about his experiences porting codes to Titan using the Cray compiler. And the summary was start by porting to OpenMP, because you just want to find the parallelism. And Cray has a nice tool to do that, this reveal tool. And then start working about moving the data, optimizing the data movement, and moving the data motion up your call tree. And that might mean moving more computation to the device because that's where the data is, and so on. But that was his point, was he was using a tool, a pretty good tool, a pretty, what word I'm looking for? A long-standing tool. Mature tool from Cray to help find the parallelism. And it doesn't, we don't have that for OpenACC. We don't have that. Now the parallelism discovery is easy. The data motion is the hard part. So that's what we're waiting for. Where's our academics in the room?
So I've heard also from Lawrence Livermore that they have tools in this space. His other point was that maybe the place to begin is by porting to OpenMP first on the CPU, and I'd like to know
Duncan,
what you think of that.
He's standing right in front of you. Let him comment. Aaron, I'm sorry.
Yeah, I think both of them already summarized that correctly, right? Porting to OpenMP on the CPU will allow you to find the parallelism, and maybe I'm channeling John LeVague a little bit here, but if you can't port it to the CPU, there's no way you're going to port it to the GPU, right? So do the easier one first. And the other main point that I made that I don't think has been mentioned yet is that really a lot of the talks that we hear talk about the syntax and how to throw some directives on loops and, hey, look, they run faster. But they don't usually talk about how do you modify loops that aren't inherently parallel, right? There can be recurrences, race conditions if they were to run parallel, right? So it's not so much about throwing directives on the loops as it is re-architecting the loops that are already there. And I think that's the hard part.
Yeah, I think my favorite part of Aaron's talk, no offense to the other 25 minutes, but was the last slide where he said, don't let your implementation dictate or restrict the parallelism in your algorithm. So.
Let's get a sense for the room. So who actually has tried using OpenACC? Okay, that's pretty good representation. Who has access to a Cray? And who has used Reveal, this tool? Wow. Okay, just a couple of people. All right, so it sounds like there's a gap in these sorts of tools. Very interesting. Okay, I'll poke another question, and then please raise your hands if you want to ask one. Fernanda, with respect, so the hackathon thing I think is kind of the most energetic and dynamic thing that's going on right now. I think there might be people in the room that have code. What do they need to do in order to get ready for a hackathon? What's an ideal person that's a candidate for a hackathon, and what should they expect to get out of it?
So if you haven't heard about the hackathon, we ran back in October. What I noticed was that a lot of users would try to use a tool, and then they would sort of get caught up in the minutia of the tool and whether or not they were making good progress in the tool. And so when I asked them back, after a training session, sort of a lecture-style training session, I asked them, hey, were you able to implement this into your workflow? And they'd tell me something like, well, I got stuck, or here, I'm in the echo zone. I got stuck, or I didn't make as much progress, so I didn't get the performance I expected, and then they would stop using the tool. And so we don't want people to stop trying to port to a GPU because they're getting stuck in the tool, or because they're getting stuck in sort of the minutia of some issues. So the hackathon came as an idea to get scientists to work on their own applications. And so the number one criteria for the hackathon was that you didn't just show up. You actually needed to have an application that you were already working on, and you had to have a team of people to work on that application with you. And what I did is to sort of eliminate the sort of pains of implementing something new is I put them together with experts, so people that knew OpenACC. A lot of them came from we had people from the lab, we had people from NVIDIA PGI, we had people from the Swiss Supercomputing Center, and we had folks from Cray too, and Aaron, John LeVague. And What they did was beforehand, about 6 weeks beforehand, they profiled their application and they worked with the mentors to sort of prepare themselves for what they were going to focus on. It was a very short period. So a successful team for these hackathons, we're having 3 this year. It turned out to be so successful for us that we decided to repeat the adventure. We're having it in other places that have GPUs. So the first one's going to be at NCSA, and the second one's going to be at the Swiss Supercomputing Center, and the third one will be again at ORNL. And the teams that we're looking for are teams that have applications, that can work with a large application team. We like them to profile their application to understand where the hotspots are, and to also be willing to make some data modification. And what I mean by modification on the data, I mean really the access patterns on their application, because it is a little bit different. But what we've also noticed, and we learned this from porting applications to Titan, is those modifications actually end up helping your application anyway. So those changes are not going to be, even though they may be global changes and painful, those changes are going to be something that is going to help your application in any sort of architecture anyway.
So one more question on that. So is it like an OpenACC thing, or what are the techniques that are going at these hackathons?
So we're primarily focused on OpenACC, but the goal is to get something on the GPU. In fact, one of the teams in the last hackathon didn't use OpenACC at all. They decided it didn't work for them, and they were going to use a library that was a CUDA-based library, and they were able to get some applications on the GPU. But because OpenACC is such an easy on-ramp to get applications and get kernels running on a GPU, and that's what we're focusing on, is trying to move people to try it. And we had some other snags. There was one team ended up using sort of a CUDA kernel, and so they built a little CUDA kernel that they called from the application. But all of these are techniques, and OpenACC is just one of those techniques to get applications running on the GPU.
So flipping back to the user experience issue. So at Oak Ridge, what are the pain points at this point in time? Or maybe reverse it. What are the successes? Where are the ones that are most likely to be successful coming from?
Well, we had a whole program to make sure they were successful. It's called CAR, the Center for Accelerated App Readiness. And we ran that before Titan came online. And a lot of people, a combination of vendor and computational scientists at Oak Ridge National Lab helped a set of, what was it, 6 applications? Mm-hmm. 6 applications. That I looked at him because he was there and when I wasn't at Oak Ridge. And about 4 of those were really, really successful in the end. What happened? There's a hand in the back?
They want you to use the mic so it gets recorded.
The profiling as prep work for the hackathon sounds like a great idea, identifying the hotspots. What about the data access patterns or the data flow? Is that anything that, are there tools that you can run on a standard app that will point out as prep work, let's say, for the hackathon, so you could enter into your hackathon with this as additional pointers of places that you would want to focus on for data reorganization?
I don't know about tools necessarily. I can't think of tools. I think experience and knowing how your access patterns may be. There's you want contiguous sections. I mean, the sort of traditional things that you look for in applications to optimize applications for access is what you're looking at.
There's no, I understand some of the ideas behind data reorganization.
Right.
But the point is, presumably the team that's entering the hackathon has relatively less experience, and then you're pairing them with an expert. Mm-hmm. And so basically this discovery process of data patterns has to occur at the point that the expert joins the team.
Right.
And it can't be prepped ahead of time so that
Right.
the expert can focus on.
Yeah, you're right. And that brings up a good point. I mean, we probably should look at tools that can give us that sort of clarification. Certainly when you start porting things already, there are tools that will show you if you're accessing things out of pattern. But there isn't anything that does what perhaps Cray Reveal might do for OpenMP. There isn't anything that tells you your data is too sparse or your data is too fragmented, and you need to do a little better job. And I don't know of anything. Do you know of any tools that
Well, I know Aaron commented that anything that is shared Mark shared in OpenMP is a candidate, and therefore he used reveal in that sense. PGProf does a little bit, but it's more based around the computational intensity and less around the actual access pattern. So I think you're right. There's room for such tools, but I'm not aware of any right off.
Okay, so this is a question for the future of OpenMP and the future of OpenACC. So you keep mentioning access patterns, access patterns.
Yeah.
So there was a talk this morning on from University of Heidelberg about how tools for restructuring to go from arrays of structures, structure arrays, so you can get the proper access pattern. So what is OpenMP and OpenACC going to be doing to help with restructuring data or directives which will actually restructure data? Since access patterns are not
shaping. I'm going to
portable.
step back.
So yeah,
You should step back.
yeah, that looks kind of
back now.
ominous, him standing up there.
So 45 years ago, before most of you were born,
This is
there
why
was
Duncan called you a
supercomputer called
senior.
the Control data. Shut up. The control data star 100. Actually, I think it was 50 years ago when they first designed it. And star 100 is mostly programmed in Fortran. They had this extensions to their language, but they had this extension for arrays called rowwise. You understand, Fortran, for historical reasons, stores arrays column major, as opposed to every other programming language in the world. But it is what it is. But I realize that sometimes you wrote your program with you're accessing things in the other way. So they said in one line you can change the layout of your array by saying rowwise, and it will store it in row major order. So it's a data layout. It wasn't a directive, it was a statement, but it's a data layout primitive in the language. And we stopped even thinking about that ever since then. And so from an abstract point of view, why is it that the way I write the program defines how it's laid out in memory? Why is that so strict? If we're going to a higher level language, isn't that something we should abstract away? And I don't mean abstract it away by rewriting it at a low level in C++. I mean abstract it away in the stinking language to begin with. So, okay, there's my religious part. Now here's the more practical part. So data layout is important, and it's not just structive arrays. It's things like you've got a big struct and you want to reorder the elements of the struct, or and if you're going to do array of destructive arrays, maybe not every element needs to be its own array. You do some grouping, or any number of things, or the way arrays are laid out, particularly in Fortran. In C, it's probably hopeless because it doesn't really have arrays, but the way these things get laid out. So we have been discussing, we've tabled it for the time being, but at least in OpenACC, I don't think it's come up in OpenMP, but I've stopped going to those meetings, of some directives to say, here's the way I declared it, here's how I want you to lay it out. Now, the downside of that is that's global. It's the same in this presentation earlier today. It's a global directive, so it changes the way it's laid out wherever you're running it on the host or the device. Now, you could compile it differently if you're compiling it only for the host. But some people think, and I'm not saying they're wrong, but they think what they want is, I wanted this data laid out this way on the host, and when I move it to the device, because the data access patterns, it's much more sensitive to the way the data is laid out, and I'm running it in parallel, perhaps in a different order than I was on the host, I want you to change the layout when you move it over there, and change it back when you bring it over here. So let me ask a question. In that, who would want that support? Who would have a definite use case for that support?
How would you do that in C or C++?
I'm sorry?
How would you do that in C or C++? In Fortran, I understand it because you have multi-dimensional arrays, right? But I think for C and C++, we need to change the standard first.
Well, okay, are you saying about arrays?
Yeah.
Yeah, I already told you, arrays are hopeless because they don't have arrays.
Right.
So we're talking about structs.
Okay.
And you would change pointers to fat pointers. You would. There are ways to do this that are not necessarily pretty and certainly not standard conforming by today's standards. But as GCC has pointed out, the compiler is the standard, and everybody follows along. Was that a question or was that a comment? Or were you raising? There's someone in back?
Okay, we'll go.
And the reason I'm asking is because we're assuming that you probably don't need that. That if you compile, you want the layout, then most people, you can live with the layout. You've laid out one way if you're using a device, and if you're not going to use a device at all, you lay it out the other way. Because changing between the two is technically really, really difficult.
Yeah, I was just wondering, what is your experience with getting scientists to transition from OpenMP to OpenACC? Like, how big's the learning curve? Because I manage an HPC cluster at a aerospace manufacturer.
Okay, let me table that. We'll come back to that one. Does anybody, so I haven't, the only hand I saw come up with my question. Okay, so there's one. So he's a big customer, so that's somewhat important. But.
Well, maybe we should ask a different question. Maybe we should ask a different question is, how many of you would be unwilling to change your data structures?
Michael, just one clarification, please.
That they're so rigid that you want to maintain the way they've been written.
My question was...
There you go. I think that's the hardest psychologically. I think that's the hardest part, is people are unwilling to change their data structures.
There's logical reasons to put them together.
No, I have a question, actually. You see, I have an array of structs. And it is much better to have a number of arrays, of course, for CUDA and all that application. I don't know, manually it is a very long struct, so I don't want to replace it with 100 arrays. So could you advise what can be done, actually? It is not a matter of even transforming the data. It is what should I do with the code?
That's exactly the problem that I'm proposing we're discussing how to solve. Because you've got a logical structure. You want the layout to match something that's appropriate for performance on the target machine. I think we need to disconnect those two.
Yeah,
and
I agree.
I think there are ways to do that.
The Coco's developer agrees.
As Christian
yeah, Christian definitely.
But I think in C and C++, we can do something in many cases.
So you're talking about this as a global mechanism.
Yes.
Is there any chance we can talk about this as a region-wise mechanism?
See, this is exactly the question I was asking, right? How many people need it, not as a global mechanism? You didn't raise your hand, so you don't get to ask that.
I did, actually. But the point is, for certain things, generally speaking, I want array of structure of arrays anyway. But every once in a while, there's something you need. You have a different data access pattern in a different between different regions, and may want to actually change it on copy.
I understand that can be important, but as I said, it's technically very, very difficult.
Can't you cover that case with just having two data structures and copy between them when needed? You know, doing explicit deep copy. I mean, in the end, from the memory perspective, right, that must be relatively equal anyway.
As long as, in the case where the layouts match, the copy is a no-op, I think he'd be happy.
But one thing for Fernanda, right, I mean, the thing about changing my data structures is, right, sure, I'm willing to change it once. Mm-hmm. But if you tell me then with your next big machine I have to change it again, I'm screwed, right?
Yeah.
In particular, if I then, for some reason, actually have to run in Oak Ridge and in Argonne at the same time, and they both want two different things, right? So I need something like...
We've been mandated different things. I want to get that clear. So for the DOE systems, we were mandated to have machines that were architecturally different. So we're not making these choices on a whim. DOE makes sure that, that the HPC environment stays healthy by making sure that we don't turn into monopolies of single architectures. So that's that part of it. But to your question, I think we've gotten lazy over the years, and in a lot of applications, with this idea of CPUs doing a very good job at prefetching. At some point in the past, we used to make sure that things didn't spill over register. At some point in the past, we used to make sure that things fit into cache. And then prefetching got really good, and we stopped caring about those things. And now it's time to care about those things again. And it doesn't matter if you're on GPU or in your ARM, it doesn't matter. All of these low-power things, because we're removing instructions to maintain low power, we have to care about these things now.
All right, I'd like to return to this gentleman who...
And I think, Fernando, you're probably the best person to answer his question as well about the reluctance of users or the ability of users to take OpenMP and use OpenACC.
And so to your question, we're an agnostic center. So I like to make everybody happy and say, use whatever makes you happy. As a center with GPUs, OpenMP is not ready for prime time on our center. The compilers aren't available yet. So the question is, what would you recommend for somebody switching from OpenMP to OpenACC is target the low-hanging fruit and see if you get good performance, and then go on from there. And it's not a very difficult, OpenACC was created so that it would have the feeling and the flavor of its predecessor, or its progeny, right? It's a progeny of OpenMP. So it looks very much the same, and I think you can do very little to just do some different pragmas and just try it in areas where you can get maybe 50% of the work done, and see how it does. And if you like the performance, then go for it.
And from the users that I've worked with, and we sit at the same center, so we've worked with a lot of the same users, is that depending on how they implemented OpenMP in their code, some of them found it practically a sed script away from being able to run OpenACC, and some of them found that they had to completely rethink things. And so it depended a little bit about how they wrote their code. But in general, I haven't encountered any who had OpenMP in their code and were unwilling to try OpenACC, because for most of them, that just meant they had done Aaron's step one, which is identify the parallelism, and then they can go from there. So it seems like for many users, it's a pretty natural fit and natural path.
And that's really not a painful step at all. Once you already have pragmas and you've already identified the parallelism, you're just switching pragmas, really.
Yeah.
I have a question related to, before you said start from OpenACC first, but what about from codes that are, let's say, 20-year-old and they have like MPI implementation? And so how can you focus on changing your data structure when you have, when you have to go so deep into MPI, into the data structures that are designed for problems that were challenging 20 years ago, but now the nature of the problem changed. So how do you assist these?
Mm-hmm. We're very experienced with that. So a little bit of history. I'm a little bit old enough to have known the history. So before the time of multi-core, there was single core, and everything was MPI. And MPI ruled the world of HPC. And then when multi-core came along, people just added more MPI ranks, and they ran those in the cores. And a lot of applications are still not threaded, running in our large systems, and they're just running just multiple MPI ranks per CPU die. And the problem, again, becomes that people aren't looking for those shared memory locations. And that's a step, I think, that we're going to have to take more often. As parallelism gets wider and wider, we're going to have to start thinking about threading our applications more and more. So, look for areas of parallelisms. There's lots of tools available out there to sort of help you identify those areas. And if you're doing a scientific application, the first thing you do is you go look for loops. Go look for big, fat loops that run a long time, and then you try, start targeting those.
So I just have two comments on that. There's no magic feather. Mm-hmm. Everybody's looking for Dumbo's magic feather. There's no magic feather. Now, you young people probably have never seen Dumbo because it's politically incorrect these days. Nevertheless. There you go.
No, it's a reboot, Carl.
Without the crows, right. And the second thing is, so one of the early success cases when they did this Center for Application Readiness for Titan was S3D. And John Levesque, who is even more senior than I am, believe it or not, and is a very smart guy, ported this code, S3D, which MPI, flat MPI. He ported it to the Titan with GPUs using OpenACC. And his process was very close to what Aaron did. First, he ported it to OpenMP, and then to get the parallelism right, and then he ported that to OpenACC, and he got a factor of 7 speed up, going from Jaguar, which was the same chassis, to Titan, which was the chassis with the GPUs. What he'll slip in there, if you pay attention, was the hybrid MPI plus OpenMP code ran twice as fast on Jaguar, which means the GPU's only got a speed up of 3.5. What it means is those flat MPI codes, it's just not as good as you think it is.
How do you compare the performance of using CUDA compared to OpenACC?
There's only a handful of codes where we can fully make that comparison, because the goal for a lot of people with OpenACC is I'm willing to do this to avoid writing something low level like CUDA. So there's only a handful of codes where we have a optimized CUDA code and a optimized OpenACC code as well. A lot of the compiler vendors will tell you, and I think you would set up and said this as well, that they feel like most of the time they should be able to get somewhere around 80% of hand-tuned CUDA. In terms of a perhaps naive CUDA conversion from one to another, you should be able to get pretty close, and then you have to start getting into some pretty low-level details to get the remaining performance. And so, would you agree with me? You can achieve good performance, but there are certain things that OpenACC is too high level to represent an optimization.
Sure. So the problems that a compiler has relative to a programmer writing in CUDA, well, A, the compiler doesn't know the application. It doesn't even know the algorithm. It only sees the program. And so all it can do is it can try to do something with the program, but it can't, for instance, change the order or the way it does anything in the algorithm. And you can, because you're a hell of a lot smarter. And you probably will. The compiler can't change the data structures, at least not yet. And you can, and you probably will. The compiler doesn't know, usually, for instance, is this array size actually a multiple of 16 or 32? And you can say, well, I'll just make it a multiple of 32. Then I don't have to worry about those edge cases. And so the other side of the coin is the compiler is tireless, and you are not. So what we encourage is use OpenACC to start, and when you have something you think is a bottleneck and you need to go to CUDA or OpenCL or whatever lower level you want, assembly language, whatever you want to do, great, go to that. But focus your efforts where the compiler is not doing as good a job as you need to.
Okay. So this is another vision future thing for both OpenACC and OpenMP. So the C++ committee is very aggressively going after parallelism native in the language. 17, maybe a hope, 21, pretty a sure thing to count on. So if C++ has all of that functionality built in the language, does OpenACC and OpenMP by the 2021 time frame become a Fortran only thing?
Fortran already has do concurrent, so C++ is trying to catch up.
Yes.
So I asked that very question to the Fortran standard committee at supercomputing last November. You have do concurrent. Does that mean OpenMP can disband and declare success? In fact, I brought that up to the OpenMP committee before OpenACC was formed. If we get parallelism in the language, does OpenMP declare success and disband? I mean, we're done, right? We've got parallelism. Why do we need directives if it's in the language? And that is a fair question. The rest of the committee didn't like that question. There are some, I have an article coming out in the next week or two in HPC Wire, and I'd like you all to read it, so it'll get to be the #1 top most read article that week, on parallel loops. And so the summary is, okay, and here's the starter point of the article. You take the do concurrent in Fortran, OMP parallel do. What's the difference between the two? Do concurrent says this is a parallel loop, where the definition of parallel loop is the iterations are independent. You can do them in any order. You can do them in parallel. You can do them backwards. You can do them inside out. It's a parallel loop. Go for it. Parallel do says take the iterations of the loop and execute them across the threads. It doesn't say it's a parallel loop. It doesn't say that they're data independent. It says spread these iterations out, and if there are any unprotected data races, well, then the behavior is undefined or implementation defined. I think in that case it's undefined. But data races between iterations are okay if it's on the same thread. So the OpenMP tells you how to execute it, but doesn't say it's parallel. Fortran says it's parallel. It doesn't tell you how to execute it. Now, in C++, there's a core language. The core language, which is basically what the compiler sees. The core language is C. I'm sorry, there's not much more there than C. It's some syntax on top, but it's just C. And then there's all the templates and the header files and the standard template library that build on top of that. And parallelism is going into the latter thing. The compiler does not see the parallelism. Someone implements parallelism someplace else. So what's the value of OpenMP or OpenACC on top of that? That's a question remaining to be seen. But it's the compilers can add value, and they're not going to see it in the C++ proposals I have seen so far.
This is the point where somebody stands up and talks about Haskell.
Yes.
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 The question was OpenACC and open source compilers, yes.
Yes, so GCC 5.0 will include OpenACC, and the extent of its support will depend on when they cut the tape and say GCC 5 is done, and the remaining parts will come in time past that. Just like with OpenMP target support, there was a basic level of support, which is ignore target, but it's there, and then they've added additional support in 5. So there will be ongoing support. But GCC 5, or if you want to go download the branch and build it yourself now, you can do so. But it is coming.
And what about LLVN? And I don't know that LLVN has OpenMP yet. Or does it?
It's in progress.
Yeah. I don't know the answer. I don't know if anyone has taken it. There was a hand up in back. Oh, there's also one.
I have the micro. I have the power. So on the comment that you made on the previous question, the fact that the compiler doesn't know about the application, so this is an intrinsic limitation of a compiler because it cannot catch very high-level information, right? The other question was on the fact that if we move from one machine to another, there is a portability issue, multi-target, and the Department of Energy probably has this the fact that they are sure, the fact that they have heterogeneity in the machines. So one way we can solve this problem is using domain-specific languages that are a higher level approach to writing compilers. In some domains, like in image processing, for example, we have examples where this is very successful, and this kind of high-level compiler are used by companies already. I know about other DSLs in computational science for finite elements, for other kind of problems, variational data simulation, and so on. My question is, what's your position with this? Do you think that this may be well accepted at some point in the future, or just a research topic that will never give something useful?
So I like DSLs a lot for all the reasons that you hint at. But it's hard to make money at it. It's hard to do this commercially, which means the community is, by definition, smaller than a general-purpose language community. And that general-purpose, that the community to which it applies are the ones that know what they want. And so they're likely to develop the language themselves, and they're not language experts. And they're probably not compiler experts either. So if I were an academic, which I'm not anymore, which I failed at, I would, and probably because I would do things like this, I would explore writing a compiler infrastructure for DSLs, so that in your DSL you express things to the compiler, saying this is the structure, and here are different options.
That already exist.
Then I'm done.
I mean, it's a recent work, but it already exists.
That sounds great. Another approach to something like that is to allow application writers to give multiple implementations of something. Say, here's a solver, here's an equivalent solver, here's an equivalent solver. You decide which one to run on which machine. And either you do tuning, or you have the compiler can choose, or you have the user choose, but some way to, when you're developing the application, expose the options that could differ.
Thanks.
While I'm walking back, I point out this kind of dialogue is happening more and more in OpenACC in our technical meetings. So if people want to participate, if they want to join, we'd welcome that additional membership.
Yep. So to go back to the notion of arrays in C++, there is the Silk array notation, and I guess it's in the new compiler. So what's your outlook on the future of that? Is that something that will be adopted more widely or not?
So this is the Silk plus array notation where you have, it looks like Fortran, in some ways it's like Fortran 90 arrays, yep. But instead of start and end, it's start and length. And it's fine. It's great. And will it get used? There are some serious limitations there, which they put in to make the implementation easier, as opposed to the expression. Like there are never any array temps, which is one of the problems with Fortran 90 array expressions. But that limits what you can write. And will it get adopted? I don't know. Is it in GCC? If it's in GCC, then people will start using it, and so yeah.
Actually, the issue of DSLs and all these directive languages coming up again makes me wonder, what are your thoughts on looking into ways to making these kind of extensions actually be portable across compilers? Defining something that will let us actually make things like this work by writing it once for the language. And somebody just mentioned that it's called C++ templates, but templates are significantly too weak to do this. So thoughts potentially from compiler writers or users?
You're asking for something portable across compilers. But do you want a DSL compiler so that it doesn't compute somehow?
Well, I mean, to some extent, in order for a DSL to be portable across compilers, there needs to be some standard for them to agree to, and DSLs tend to be to such a small community that they are both designing the language and whatever interprets the language.
So compiled onto LLVN IR. I'm making that up as I go. I don't know.
So hang on, are you thinking that there should be extensions to the IR to do this?
Does it need an extension? At that point, the
For DSLs.
DES part may have been resolved. C is your portable assembly language.
All right. So I have another prompt unless this lively discussion keeps going. I think we sort of sidestepped some of the just general questions around best practices, if you like, between OpenMP and OpenACC. Are there best practices that this crowd should follow? Today it would be to spread OpenMP on the CPU versus OpenACC on the GPU.
First best practices come to a hackathon.
Yes.
Yeah.
Yes. Aaron was one of our mentors. Thank you, Aaron.
That's a lot of fun. Put in 16-hour days.
Woo! Free food. 3 meals a day, too. Come for the food. Stay for the hackathon. Best practices. I don't know. I don't know that I've seen enough examples yet on best practices for either of these for HPC. I know that sounds weird.
So one thing that I advocate in my talks and in a coming document that I hope to be published soon around OpenACC best practices is to take a kind of an incremental layered approach. You have accelerated libraries available to you, and if you can use those libraries, great. Someone else already did the hard work for you. You're done. And if that's not good enough, then you have compiler directives that are simple. You can use Amdahl's law to your advantage and rapidly accelerate a lot of your code, just whether it's still valid or not. We can go back to your article, but use that to your advantage, accelerate as much of your code as possible very quickly, And then the next layer, or the next incremental part, is to then to further tune, whether it be with directives or with low-level languages. But even within each of those steps, if you want to watch my talk on Wednesday, to take an approach of incrementally adding to your code and playing good game whack-a-mole.
What I'm keying on here is that, like, for example, when we talk about the kernels directive, if I'm trying to write OpenACC code that one day is good OpenMP code as well, do I use the kernels directive?
Yeah, I mean, so that's why I was saying I didn't feel like there was enough example, because even OpenMP, there's so many ways you can do one thing. And even for OpenACC, we have multiple ways too.
So I was hoping either Chris or Guido would make it to this, because they're in the process of trying to migrate between OpenACC and OpenMP within the Spec Excel benchmarks and forming best practices there, where really they're focusing on use a limited subset of both specifications that maps well to each other. Although Chris and I differ a little bit in our opinion about what that subset should be, but still there are features in each that, there's features in OpenACC that aren't available yet, but if you limit yourself to ACC parallel loop everywhere, then you've got a pretty direct mapping. If you're, you really just need to look at what functionality is available. If you're doing, everything is a parallel 4 rather than a parallel and a bunch of 4s, that it's simpler for the compiler with those combined constructs. So really, I think you have to kind of limit yourself a little bit in scope, but it can be done. And we're still kind of forming those ideas and learning from really a lot from the experience within Spec Excel of what that limited subset of features is today. And we hope it will become less limited in the future.
So let me jump in here. So for best practices, if you're looking at, if you're not as old as I am, your application is going to outlive your machine. Machine lives for years, applications live for decades. Nobody could have predicted 10 years ago that we would be talking about a second generation of a top-level supercomputer using GPUs as accelerators. I defy anybody to defend that. And I defy you to predict what the top machine will look like 10 years from now. We have hints, maybe, but as Fernanda said, we got lazy from about 1995 till about 2008, because all the machines, they just looked all like, every machine looked like every other machine at the high-end supercomputing level. Well, that's no longer true. Data structure design does matter. Access patterns do matter. Scalable parallelism really, really matters. Lots and lots of parallelism. Synchronization, get it out. Okay? Any synchronization that's a barrier to progress, it's a barrier to parallelism, use as little of it as possible. You want as much asynchrony, you want as much, okay, parallel loops. Nested parallel loops is where I'm thinking you need to go. Because you don't know what that program's going to be running on 10 or 20 years from now. And if it doesn't work, it won't be running anywhere.
Yeah, I've encountered a lot of users, they say, well, we went through the pain of rewriting our code 25 years ago, and we don't want to rewrite it again today. So you know what? You're going to rewrite it today because otherwise it's not going to perform. And you know what? 25 years from now, you're probably going to rewrite it again because change is inevitable. We can make some speculation that 10 years from now, it's probably still going to be a very parallel machine. So I think it's safe to say you need to develop parallel code, but the specifics are the things. And that's why OpenACC and some of the work in OpenMP as well, but specifically in OpenACC, we want to design something that is high level enough that you're expressing the parallelism without hamstringing the compiler from making smart decisions about, oh, I see you're running on a more parallel or a less parallel architecture. And so focusing on the commonality, the parallelism, and the data locality helps you, mitigate this change and the change that's going to come after that.
I mean, I still find myself trying to convince users that things are going to get wider and wider. They still think of machines that are coming out as just CPUs, and I point to phones and I go, like, your phone has more cores. Like, when your phone starts getting extra cores, things are getting wider, and then things are getting low power. So you're going to have to start thinking about that's what architectures are going to look like in the future. It just happens that the GPU is this sort of frankly, it's the absurd, already there version of what's going to look like in the future. But they're coming from a CPU perspective, so they're thinking that, no, this is just a temporary thing. Later on, things are going to change, and it's not. We've already been there. It's just the GPUs have been there because of the purpose that they were built for in the beginning.
So in terms of increasing parallelism and hierarchical parallelism and exploiting parallelism wherever you can find it, I have noticed that discussions have been constrained to two models here. One that's loop-driven, whereas you, certainly with OpenMP and also with OpenACC, you can actually have do less type of parallel regions. And the other constraint that I have seen is one in which you are just expressing the parallelism within one method. So you are substituting OpenMP for OpenACC or the other way around, while they can and should probably live together. So how do you see that evolving? How can we exploit that?
Evolving into different types of parallelism, you're saying?
Well, the support of it. So for example, we're talking all the time about substituting OpenMP by OpenACC, whereas probably that is not what you want to do. You probably want to do OpenMP for CPU and OpenMP for GPU, one within underneath the other.
I don't think that's a problem.
Yeah, they can certainly coexist, and in fact, there's no reason why it couldn't be OpenACC on the host with OpenACC for the accelerator underneath it. I mean, so I'm not completely sure what you're getting at, Roberto.
I think part of this might be in the runtime support mixing of directives.
Runtime support mixing of directives, mixing with the eventual coming parallel language features as well, and mixing them together, and all of that mixing and.
Well, GTC is going to use the same runtime, isn't it?
Yeah, I believe
the same runtime,
the compilers that I know of that are implementing both OpenMP for target and OpenACC have a coherent runtime, and so they will live together. In fact, you can mix OpenMP for target and OpenACC on the device.
You can mix the data, but not the parallelism.
Well, I don't see why.
At least today, that's okay.
So related to the previous question, what I hear often from people, especially from computational scientists, is that computer science has failed them because because there is no real alternative now when they are told to move now, to do it now. And I see it as a bit of a danger to come with OpenACC and OpenMP and compete and argue what is best, which one is better, which one is worse, instead of providing a way that works in the intermediate phase and then figure out a way that works on the long term. So how do you see OpenACC and OpenMP living together side by side and not even having figured out whether it should be CPUs for one and...
That's what OpenACC was. It was the intermediate. OpenMP wasn't ready at the time to
but
target...
why not invest in getting OpenMP ready instead of...
We did, but it wasn't ready. Just the standard wasn't moving fast enough. That's what OpenACC was. It was the intermediate. It is the playground. It is where we try new things.
But then what do you tell computational scientists? What to use?
We tell them
what should they use?
We tell them to target whatever it is that they're ready for right now. And if they like to target...
Which technology should they use?
If they're going to run on Titan, they should use OpenACC. That's what's ready now.
Why?
Because that's what's ready now.
But then they should throw away their code.
I didn't say they have to throw away their code. I said if they like to target Titan, to run on Titan, they need to use OpenACC.
But wait a second. The Titan is dying. I mean,
what
should they use?
It's going to be available until 2019. The next supercomputer is going to have multiple GPUs. It's not dying.
Summit is dying.
I'm talking about those people who may have a Fortran only code and they need to act now. And
yeah,
so
they can use OpenACC with Fortran.
into porting to Titan with OpenACC.
Absolutely.
And to realize that maybe IBM prefers OpenMP, so on the next machine it will be OpenMP.
We're going to have a PGI compiler that's going to make that available for them, and IBM might make it available. We're not at that point yet, but right now, if they want to target Titan, they can have OpenACC, and they can target Titan.
Sadly, I think these are the answers exactly that computational scientists, physicists, chemists will find inadequate, and they will say, I'm going to wait. And
then they're not going to get the performance of Titan. I mean, if they want to do a big problem that scales across 18,000 nodes, and they have an application that scales across 18,000 nodes, and they want to do that sort of problem, then they need to take advantage of the flops that are available on the GPUs. And the way to do that is to do it with OpenACC. Or they can try CUDA.
Yeah. And, that will continue to be the answer on Summit as well, and we believe that will be the answer on other platforms on the DOE as well, that if you develop your code on Titan using OpenACC, it will be available to you on Summit. We believe it will be available to you on other DOE platforms and other university platforms as well.
I mean, I serve on both committees. That means that we have a commitment right now to support things that make, to give scientists accessibility to the technology.
So
we don't have time to go and develop standards into languages. Those things only the machines last 5 years. We needed something that moved quicker. That's what OpenACC was. It was the intermediate.
Yeah. So I think part of the answer might be actually what has been discussed before, that it's not about the, the syntax of the declarations or anything like you. The idea would be if you change your application now to OpenACC, I'm not saying that I believe that's 100% true, but you port your application to use OpenACC efficiently now, and then OpenMP, the more mature, bigger, longer running standard catches up, then you change hopefully a little bit of your pragmas, but your application in general should be ready to have high parallelism.
Our hope is that at a point in the future, OpenMP will mature to the point that if you've developed the OpenACC, you will be able to make that conversion. Does that mean you should? Does that mean you will have to? No, we would like to see OpenACC continue and live on, and if you are going to make the change from OpenACC to OpenMP in the future, I hope it's for reasons other than spelling. I hope it's for reasons that they are providing something that you believe OpenACC is not, but we believe OpenACC addresses the issues necessary on parallel platforms in a way that today is better than what OpenMP is providing, and OpenMP is still catching up, and eventually they are converging. And it doesn't matter to me whether the two lines converge into one or converge into two that are very close. Just like C and C++ are very close, but they are not the same.
But can I make a slightly different comparison? Because
sure.
Hey, we're application developers, and if you look on the graphics side of things, I think something that set the entire community back like half a decade is that Microsoft decided to do DirectX instead of OpenCL. And you're kind of doing the same thing here. So that, instead of OpenGL. And gradually, we're now seeing everybody getting back into OpenGL by having a standard and then letting vendors have extensions of the standards. But the point is that those extensions gradually evolve to become part of the standard. It's not a completely orthogonal set of a completely orthogonal set of features that diverge from the standard and tend to diverge more and more over the years. And it really worries me that we might start to see the same thing happening here.
Well, your point is well taken. I think we disagree with your conclusion.
Yeah, I mean, we are that overlap of the Venn diagram that I mentioned. We are working hard. Two of the three of us here are on the calls each week to make sure that the lines are converging and not diverging. And that's we are looking at features as we're adding them to OpenACC and saying, is this necessary? Is this portable? And we're looking and saying, we are mindful of what OpenMP is doing, just like OpenMP is mindful of OpenACC is doing. And there are times we look at, from both sides, we look at what they're doing and say, we don't want to do something that's fundamentally incompatible. If they've already done something, we want to ensure that we're not going to do something that's incompatible unless there's a really good reason to do so. So we are working to make sure that the lines are not diverging.
There's a lot of overlap between us serving on those committees. And I think what I'd like to ask is an assumption of goodwill. I think there's been an assumption of bad will toward these two standards, and we serve. I mean, the overlap is huge, and I like an assumption of goodwill that we're trying to do what's right. It's just that one standard is trying to move a little faster to make sure that we have something available for users. And the other standard is still, I think, trying to sort of understand where this is where the coverage is, right? So the OpenMP standard, not only is it more mature, but it also has a lot of other clients that it has to serve, right? It's not just CPU for them. In fact, there are people from AMD there, Texas Instruments, Intel, IBM, and all of these folks have technologies that are essentially vastly different. And so they're going to naturally move slower because they're trying to serve all of these other technologies, all of these other architectures. And that's okay. But at that moment, for a center like ours, we needed something that worked for the specific architecture that was Titan. And so for that moment, we supported OpenACC because we needed something that worked then. And right now, we're just now getting to the point, and we still don't have compilers. Here we are, 2015. We still don't have compilers that can compile OpenMP on the GPU for us.
Yeah, the discussion's interesting because sometimes it's the reality of the compilers that exist versus the paper standard, which has not been implemented.
Yeah,
at least
exactly.
not in the same place.
Yeah,
so
standards may exist,
time.
right? But that doesn't mean the compilers, and that's another thing too I like for folks to understand is that a standard is one thing, and you can create standards, and you can make do concurrent. How many people are using do concurrent? That doesn't mean the compiler is going to implement that standard.
What I like to think of, though, is that with all goodwill, we are out there a little earlier, and there are things to be learned from that early developer experience. That's the contribution that OpenACC is making to OpenMP. What they make of it, I think, is a subject for long debate in that committee.
One other minor plug for PGI. So people ask us, well, what if OpenMP overtakes and absorbs OpenACC? Do I have to rewrite all my code? So the difference between a commercial compiler and some open source POS is with a commercial compiler, customers demand support. Predecessor to OpenMP, one of the widely used predecessors was the SGI do-across directive, which was actually designed at Sequent, which was a little parallel processing company in the mid-'80s in Portland, outside Portland. PGI still supports the SGI do-across because, well, there's no reason to get rid of it. It's not incompatible with anything else. Customers demand that their codes don't break.
So with that, I think we need...
I think the whole point is that directives and libraries, that notion is really not going to change that much. If you're leveraging libraries, you've already removed, you're future-proofed essentially what you're doing. The notion of using directives, whether it's OpenMP, OpenACC, or whatever it is, the notion of using directives is already at a high level of abstraction. So the future-proofing of that, I think that will take care of itself because nobody wants to break existing codes when they've done that. I think the directives approach is that broad parallelism that we have to deal with. And that is the solution to that. So I don't think that's going to go away. I don't think you have to worry about the future of that because of that abstraction. Nobody's going to break those codes.
And if you're adding just 10%, what was it? 10% was the mini MD example. I mean, if you're adding a few pragmas so that you can utilize technology now.
All right. I'm afraid I have to bring this to a close. I want to thank the audience for participating so heavily in this, and I'd also like to thank our panel as well.